Hello, dear students. I am Samir Velankar. I welcome all of you to this another question on quicksort asked in GATE 2008. If you have watched the earlier video, which was around about 20 minutes, and we have solved a GATE question which was very challenging about n by fourth smallest element, then I'll tell you that this is going to be very easy for you. Straight away, you will tell me what's the answer here. Consider the quicksort algorithm. Sorry. Suppose there is a procedure for finding a pivot element which splits the list into two sublists, each of which contains at least one-fifth of elements. Then Tn be the number of comparisons required to sort n elements. Then what will be Tn? Now, given an array of size n, let's say there is some array which is of size n. And what they are saying, size is n, they are saying that we have an algorithm which selects a pivot, some pivot. We have been always selecting pivot as leftmost, isn't it? But they are selecting pivot such that after doing partitioning, the array will be split into two sublists, each containing at least, you note, each containing at least one-fifth of the elements. So the pivot will be fixed somewhere. This will be the partition in place, and one partition will be of size n by 5, and other partition obviously will contain rest of the elements, which is 4n by 5. If you add both of them, n by 5 and 4n by 5, you are going to get 5n by 5, which is n, correct or not? So at least n by 5 means one of the partitions will contain n by 5 elements and other will contain rest of the elements. And each time this will happen because they are efficiently selecting a pivot which will split the array into two halves, or sorry, two partitions, one of size at least n by 5 and other of size 4n by 5. So what is going to be the number of comparisons if Tn represents the number of comparisons? What we will say is that n n is the time needed to partition, isn't it? First we will partition, and you know partition works in the order of n, and then we will like to sort this n by 5 elements. So that's the number of time or time taken to sort n by 5 elements, and we will also sort this 4n by 5 elements, which is time taken to sort 4n by 5 elements is represented by t 4n by 5. So the total time is n time taken to partition plus Tn by 5 plus T 4n by 5. So B is the correct answer. No more discussion needed, isn't it? It was so simple. Now let's see the next question. GATE 2006. What they are asking is the median of n elements. Median of n elements can be found in ON time. So there exists an algorithm which finds median of n elements in ON time. They have not given that algorithm. Which one of the following is the correct about complexity of quicksort? Now just imagine that we have 8 elements, okay? And some 8 elements are somewhat like this. I will purposely take 1 to 8 elements. Just imagine that I have 8, 6, 2, 1, then I have 3, 4, and then I have 7, 1, 2, 3, 4, and 5. Okay, let's take 9, one more element, and 9 is over here. So n is 9 over here. Number of elements are 9, and I have purposely taken elements from 1 to 9. Now they are saying that we have selected the median of this. Okay, and the median of this is selected efficiently using the time on. Now we have got the elements actually as 1, 2, 3, 4, 5, 6, 7, 8, 9, isn't it? And the median is going to be 4 or median is going to be 5. Both are the eligible candidates. Oh yes, oh 5 is the median. Okay, I'm so sorry, because it divides it into 1, 2, 3, 4 and 6, 7, 8, 9. I hope you know what is median. Median is the midpoint or the or the midpoint of the sorted array. So here this array is not yet sorted, but you will agree that if the elements are 1 to 9, then the median is 5. So this is the pivot they are selecting, isn't it? This is the pivot. And you have an algorithm, they are saying, which works in the order of n. So this 5 will be fixed at proper place by partition function. And now with, from our first video of the gate question, you don't have to change the partition function at all. What you can do is, before running the partition function, you can put this pivot at the leftmost, and then 8 obviously will go at the place of pivot. And now you call partition, you know that partition always fixes the leftmost element, isn't it? So run your usual partition process and 5 will be fixed at proper place. So you only tell me where will be 5 fixed. Remember, 5 was the median of 1 to 9, isn't it? So 5 will be fixed in such a way that the left of 5 will be 1, 2, 3, 4, and right of 5 will be 6, 7, 8, 9. Come on, 5 must go at this place of the array. The place is 0, 1, 2, 3, 4, fourth place. 5 must go, isn't it? Because it was median and this was the best place for 5. I am not saying that the left elements of this will be 1, 2, 3, 4. They might be 3, 2, 1, 4, because their relative positions are not yet sorted. And the right of this, that is 6, 7, 8, 9, may not be sorted like this. It might be 7, 6, 9, 8. But hello, next time even this part is going to be sorted and the right part is also going to be sorted. So what do you observe? I hope you observed it enough. If you select median and fix it at proper place, then you are going to get partition of size n by 2 and partition of size n by 2, and then you will sort them. Great, isn't it? If you can fix the median at proper place, you're always going to get the two partitions of equal size, because the median will be in the middle of the array, isn't it? And then the left will contain n by 2, right will contain n by 2. So the recurrence relation that will arise from here will be Tn, Tn is equal to n. This is the time taken to partition, isn't it? First of all, you will partition plus time taken to sort n by 2 elements plus time taken to sort n by 2 elements, which is nothing but time taken to sort two partitions of size n by 2 plus n. This is the recurrence relation we get. And now on solving the recurrence relation, we are going to get O n log n. Observe, this can be solved by Master's theorem, because A is 2, correct? This is A is 2, B is 2, here is B, and n raised to k was the usual order written, and k is 1 over here, and log raised to p of n, so p is 0 here because log term is missing. And you can see that according to Master's theorem, we are having case 2, because a here is equal to b raised to k, 2 is equal to 2 raised to 1. And within case 2 of Master's theorem, we had a sub case. If P is greater than or equal to minus 1, as you see, this is true here. P is greater than or equal to minus 1 because P is 0. 0 is greater than or equal to minus 1. Then Tn is given as theta n raised to log of a to the base b into log raised to p plus 1 of n. Just refer Master's theorem. Just refer Master's theorem. If you have lost the touch, then Tn will be equal to theta n raised to log of 2 to the base 2. A and B are 2 each. So this is going to be n raised to 1. And log of n raised to p plus 1. Log raised to p plus 1. But p is 0. So 0 plus 1, that is log n. So the answer is n log n. I hope this was not necessary actually, because once we know this recurrence relation, I knew that you have ability to solve the recurrence relation using Master's theorem, and this is the answer. But the fun part was the median selected as pivot will always give you two partitions of equal size, n by 2 and n by 2. So we will get a perfect ideal recurrence relation of two partitions of equal size. Thank you very much.